Welcome to Modern Physics Lab number 3, Black Hole Orbit. So we're given a star's orbit around a black hole and we need to find the mass of this black hole. So we're going to take a star's motion data, find the net force from that data, and then use that to find the black hole's mass. The fundamental physics concept that we're dealing here with will be Newton's second law in its most popular form, the momentum principle. And we're going to actually start with two major assumptions that the net force acting on our system, which in this case will be a regular star, will only be the force of gravitational attraction from the black hole. Also, we're going to assume that our black hole is relatively stationary compared to the star. And then we're going to go over a couple other things and answer some questions based on the data that we analyze. So our fundamental physics principle here again is Newton's second law, or just the momentum principle. And this is the same thing that we've used in the first two labs, with a little bit of algebra to get it from this form where we're using the net force to really tell us something about the motion of the object and the velocity of the object. We've done some nice algebra so we can actually use the motion data, in this case represented by our change in momentum over our change in time, and having that be equal to our net force. So again, we're using our motion data to tell us something about the overall interactions acting on our system. So here, just something about our axis selection. You have our delta P, delta T parallel axis, which will always be pointing in the direction of the motion of the object. And then you have our delta P, delta T parallel axis, which will be pointing in the perpendicular direction from this axis. Interesting thing also to note here with delta P, delta T perpendicular is that it will always be pointing toward the center of the kissing circle, which is a circle that can be drawn with one point tangent to any point on the trajectory of the motion of the system. So what does this mean? So dp dt, or delta p delta t, and f net. So we know algebraically, mathematically they're related. But some other things to kind of note here is that when you break it down into their individual components, the delta p delta t really kind of represents the object speeding up or slowing down if delta p delta t parallel is a non-zero value, and if delta p delta t perpendicular is non-zero, that represents the object changing direction. So what this really is here you have the motion data, and here you have the interaction. You have the net force. So you can kind of think of this as, on the left side, this is the effect. This is what happens. You have this change in momentum, this change in motion. And here you have F net, which really gives you the causes. This is the total sum of all your interactions on the object. So kind of think of it that way, effects and causes. So our initial conditions, you have the star's mass, you have the black hole's position, you have this G constant, you have your delta T, which is basically a 1 full day put in seconds, and then you have this time value. Our time is going to start at 0. So some other things, these are the equations I use to actually find our unknown black hole mass. And here all I did was I took the magnitude of our force of gravitational attraction, and I just went and used algebra to solve for this unknown black hole mass. And again, this is an approximation of the G constant I use. This is the actual code I used here. And again, the R vector we used was, we found that by doing our star's position minusing our black hole's position. So here's our computational model. Notice on the left you have our CSV data. On the right you have our actual Python code. We read this in and we see these three arrows here, and the three arrows represent our net force perpendicular, our net force parallel component, and just our overall net force. And you see here that we're actually able to find the mass of our black hole. And this mass was correct. We went and we checked this with some predetermined value, so that's great. We know that our math and our physics is right here. So let's take another question. So let's imagine that we took out the first black hole and we put in a different black hole, and we're going to assume that the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. So could we find the mass of the new black hole? Well, the answer is yes. We know we have the same position data, so our acceleration here won't change. We also will know the net force because we are able to calculate the force of a gravitational attraction on our star. And so with that information, knowing the acceleration, or knowing and we know this again from our motion data, and then also being able to find the net force, that means that we can always solve for a new mass. So in this case, the answer to the question is yes. That's our lab.